So let's remember that we said Oersted discovered, completely accidentally in a classroom, that if a wire carries current, it makes a magnetic field. And he found that just by connecting a circuit. He had a compass laying nearby and he saw that the compass deflected. So this begs the question, does it work in reverse? And that's what Faraday studied. I've got a demo of what he studied right here. The video is backwards. Please forgive me. It's because I made the video on my phone and apparently I'm not that good at it.
This is going to be a demo of probably my favorite physics effect ever. When I learned about this back in my first year university, this was the point where I made the decision, I have to study physics because this is just so cool. I need to be doing this for the rest of my life. So what this is called a galvanometer. It can measure either potential or current. I'm going to use it to measure current. So we already know that if we have a wire carrying current, there is going to be a magnetic field around that current carrying wire. So a current makes a magnetic field. Faraday asked, is the flip side true? If we have a magnetic field, does that make a current? So let's see what the answer to that question is. So what I've got here is a solenoid, a bunch of loops of coils of wire. So I'm going to hook up my solenoid to my ammeter so I can measure the current that's flowing through the solenoid. Okay, I've got it hooked up. Right now it says that the current is through it is 0. The center needle is off a little bit. The thing is really old. It gets out of line pretty fast. Next, what I have here is just a stack of rare earth magnets. They have a really strong magnetic field. I'm going to take the magnetic field and I'm going to move it in the vicinity of the solenoid. I'm going to poke it right down through the center. So you watch the galvanometer as I push the magnet in. Okay, when I push it in, my meter deflected this way. When I pull it out, it deflects that way. So in, out. That's kind of cool. So yes, when I put the magnetic field near my wire, I got current. That's kind of amazing. Turn my magnet over, I'll push it in again. Now it goes the other way. So the direction of magnetic field matters. It affects the direction of current. What if I push it in really fast? Okay, it deflects really big. What if I take it out really slow? It doesn't deflect so much. This is kind of telling us something. What if I put it in and I don't move it at all? So I put it in, the needle comes back. Okay, so this is super interesting. It's not just that the magnetic field makes a current, it has to be the change in magnetic field. So this is kind of the heart of energy generation. If you can change a magnetic field, you can get current. And this is pretty clean energy, right? I didn't produce any greenhouse gases doing this. So I think this is a really neat effect and worth our time to look at.
So the answer to Faraday's question then, does a magnetic field create a current, is definitely yes, but only if the magnetic field changes. So yes, but only if B changes. So Faraday, in fact, also discovered this somewhat serendipitously. He opened and closed a switch on one wire, and he saw a galvanometer connected to another circuit flicker. So he actually discovered a transformer completely by accident. Again, Faraday is probably not the only guy who ever studied this, but he is the one who made it into the history books. Next, let's explain the effect that Faraday observed. So let's start by taking a conducting bar, that's the gray bar in our picture, and let's place it in a magnetic field that points into the page. So those are the blue X's in the picture. Let's pull the bar to the right with some velocity v. It's a conducting bar, that means it's full of charges, and those charges are going to be allowed to move. Let's say that our bar has length L. Okay, so what happens as we move our bar to the right? So every charge in that bar is going to feel a magnetic force. Remember, magnetic force equals QV cross B. So the charges, whether positive or negative, will feel a force with magnitude FB equals Q VB, times sine of 90 degrees. Remember, the angle is between V and B, and in this case, those are perpendicular. What about the direction of the force? So if we think about a positive charge, if we apply our right-hand rule, we put our thumb with our V, that's to the right. We put our index finger with our B, that's into the page. We should see our middle finger point up. So the magnetic force points straight up for a positive charge. So the direction, positive charge, FB is up. What about for a negative charge? Well, if we had a little negative charge, we would do our right-hand rule. And remember, right-hand rule applies to a positive charge, a negative charge is opposite. So the magnetic force on a negative charge points straight down. So what happens if there's an upward force on a positive charge? Well, it means the positive charge moves up. And if there's a downward force on the negative charge moves down. So if we're looking at our picture, all of our positive charges drift up towards the top. All of our negative charges drift down towards the bottom. The result is that our charges separate. And what do we get if we have a line of positive charge on top and a line of negative charge on bottom? That's an electric field. And if we have an electric field applied across some distance, that also results in an electric potential. And I guess we can fully say an electric potential difference. Okay, how big is that electric potential difference? Well, we remember that electric potential is equal to the field times the distance of separation between the 2 points. Okay, some notes about the notation here. We use epsilon for the electric potential, and we call it EMF. So epsilon is our induced electric potential. Also called EMF. Historically, EMF was called electromotive force because the scientists who studied this thought about the forces and they thought that what they observed was a force. We now know that's a potential, so we don't really say electromotive force anymore. We just straight up say EMF. The really important thing, or an important thing here, is that we only have an induced potential or an induced EMF. So we only have epsilon when the bar moves. So if the bar doesn't move, it means velocity equals 0, force is 0, no separation of charge, no field, no potential. Okay, next, let's see if we can find the size of that induced potential. So if we're asking how big the induced potential is, let's ask what happens over time. We know that as we pull the bar to the right, the force on the positive charges points up and the negative points down. That leads to our positive drifting towards the top and our negative drifting towards the bottom. And then over time, eventually in the middle, there's going to be some charge. It'll feel a magnetic force pointing up. That magnetic force is QV cross B. And it also feels an electric force pointing down. That electric force is Q times E, where the electric field points straight downwards because the electric field points from positive to negative. At some point, you get enough charge built up on either side that your electric field gets bigger and bigger, and at some point, the electric force equals the magnetic force, and we reach a steady state. So those charges drift and separate until the electric field is big enough such that the electric force is the same size as the magnetic force. When that happens, those charges stop drifting, they stop moving up and down, and the net force is going to be equal to 0. We're going to use that idea to find the size of our induced potential. Okay, so let's write down what it means that we have steady state. Steady state. That means that the net force on those charges in the bar is equal to 0. The two forces we have are the magnetic force and the electric force. So there's our vector expression. The magnetic force points up, so we'll say plus FB. The electric force points down, we'll say minus FE equals 0. We'll use that FB is QV cross B, so the magnitude of FB is QVB. So magnitude of FB equals QVB, and the magnitude of the electric force is QE. Let's put that in our expression. QVB minus QE equals 0. Okay, so now what we see here is we can divide both sides by Q, and that leads us to VB, so the speed of our bar times the strength of the magnetic field, equals the electric field. That's our condition when we reach steady state. Now let's layer in our induced potential. The induced potential is the electric field times the length, so the electric field is induced potential divided by the length. So that comes from potential equals field times length. Okay, so now all we have to do is solve that expression for our induced potential. The induced potential is equal to the strength of the field times the length of the bar times the speed of the bar. So that gives us the expression for the induced potential in this situation. So here's just a quickie example for you to try to make sure you get the idea of which way the forces point. We have a metal bar moving through a magnetic field. The dots mean that B is out of the page. And the question is, which of these choices represents what happens to the charge? So if you want to think about this, let's imagine if we had a positive charge right here, what would be the direction of the magnetic force? So grab your right hand, your thumb should go with your V. You should point your finger, your index finger with your magnetic field. So your index finger should point towards your face while your thumb points towards the floor. Your stuck out middle finger should point towards the left side of the page. So a positive charge is going to be pulled to the left, and a negative charge would have a force that's opposite that. The negative charges would get pushed towards the right. So if we look at our options, that corresponds to B. Let's do an example now with some numbers. We have an isolated conducting rod with a length of 8 centimeters. So a rod that looks like this. It's oriented parallel to the x-axis, so I'm going to put my coordinate system in here. So x is horizontal, y is vertical, positive z is out of the page. It moves in a plus y direction at 3.9 meters per second, so there's my velocity. In a uniform magnetic field of magnitude 0.6 teslas that points in the negative z. Negative z is into the page, so our magnetic field can be represented by some x's. Okay, so there's the motion of our bar in the field. Let's write down what the field is equal to. And let's include our length in our list. We'll write down our length in meters instead of centimeters. Okay, part A. Find the magnitude of the motional EMF in the rod. Motional EMF, that's the EMF or the induced potential, induced because the rod is in motion. So this is asking us to find our induced EMF epsilon. We know that our induced EMF, by following the steps on the previous slide, is the magnitude of the field times the length times the magnitude of the velocity. So 0.6 teslas times 0.08 meters times 3.90 meters per second gives us an induced potential over the two ends of that rod of 0.1872 volts, or 0.187 to 3 sig figs. Okay, part B. What is the magnitude and the direction of the electric field produced in the rod or induced in the rod? So to find the magnitude, we'll remember that electric field is potential divided by the separation distance. So we'll put in our induced potential, 0.1872 volts. It's divided by the length of the rod because the charges move to the opposite ends. That's how far they're separated by, 0.08 meters. When we do that in the calculator, we get 2.34 volts per meter. That's the magnitude of the electric field. To get the direction, we know that electric field points from positive charge to negative. So let's see which way the charges move. A positive charge here will feel a force. Let's do our right-hand rule. Our thumb is our velocity. It points towards the ceiling. Our index finger is our magnetic field, points away from us. It looks like we're making a finger gun shooting at our computer screen. Stick out your middle finger. It should point towards the left. So the magnetic force on a positive charge is to the left. That tells us that positive charges will build up on the left end of the rod. The direction of force on a negative charge is opposite that. It's going to be to the right, so our negative charges will build up on the right end of the rod. Electric field points from positive to negative, so it's going to point to the right. So our electric field vector then is 2.34 volts per meter in the positive x direction, or I hat. Here's a problem that just ramps it up a notch. I'm going to suggest that you do this one for a homework problem. I won't work through it in a video, but I will write up a solution and post it. Let's do a problem now that looks a little different, but works on the same principles. We have a metal bar with length L. So let's draw in that length. It's rotating with angular velocity omega. It doesn't say what the direction of rotation is, so I'm just going to assume it's clockwise. There's our angular velocity, about a pivot point at one end of the bar. So let's put a pivot point right here. A uniform magnetic field is perpendicular to the plane of rotation. The x's in the picture show that it's into the page. What is the potential difference between the ends of the bar? So let's think about what's happening on any little positive charge in the bar. Our bar is rotating, so the velocity of this charge is going to be perpendicular to the bar, or a tangent to the circle. So there's the velocity of that charge at that instant in time. We know that it's going to feel a magnetic force. Magnetic force equals QV cross B. The direction of that magnetic force, you can do your right-hand rule. You stick your thumb in the direction of V, so sort of down and to the right. Your index finger is into the page. Your magnetic force points towards the upper end of the bar. So there's the magnetic force. If you don't like the right-hand rule, you could always do it the cross product to find that's true as well. A result of the magnetic force is that positive charge will drift towards the upper end of the rod, and negative charge will drift towards the lower end. That separation of charge results in an electric field, which will go from the positive to the negative. And if we have an electric field, every positive charge will feel an electric force. There's the electric force. We remember that electric force is charge times field. Okay, when our bar reaches steady state, we'll have that the magnitude of the magnetic force will be equal to the magnitude of the electric force. Magnitude of the magnetic force is QVB. The angle between V and B is 90, so our sine theta there is sine 90. That's equal to 1. Equals Q times E. Got a Q on both sides. We can divide through by the charge. And it tells us that the electric field is equal to V times B. This is similar to everything we've done before. Here we'll layer in one additional part. We can remember from circular motion that the angular velocity omega and the linear speed v are related. The linear speed v is omega, the angular velocity, times the distance from the pivot. We can label that in our picture. Okay, so our electric field is V times B, which is equal to omega R times B. All right, there's an expression for our electric field. We're trying to find the potential difference. Normally we'd say potential difference is E times L, but here our distance is not, our electric field depends on the distance. So the electric field is not constant over the bar. It depends on how far away you are from the end. So rather than doing delta V is E times L, we're going to have to use the integral form. So the potential difference is minus the integral of the component of electric field times the component of distance. So that's the electric field over the length. So that comes from our expression for electric field. Delta V is E dot ds. Here our electric field is in the radial direction, so it's ER times dr. Over our length integral, the limits are going to be from one end of the rod to the other, so from L to 0. Let's pop in what our E is equal to. So that's omega times R times B times dr from L to 0. Take our omega B out front. We've got R dr. The integral of R dr is R squared over 2. Evaluated at 0 and L. So that's minus omega B times L squared over 2. So the potential difference across the two ends of the rod, and that's the induced potential difference, it comes from moving the rod in a magnetic field, equals omega times B times L squared over 2. Okay, so same kind of problem, just a slightly different setup.